Okay, what time is it? Guess we have maybe, well, 10:30, we can start. So last night I had a dream that I gave a really bad lecture. And this morning at 8:30 in my other course, I gave a really bad lecture. So hopefully that was it. And now it's out of my system. We're going to try to finish all the technical stuff about, special kinds of neighborhoods in a Riemannian manifold, the rest of chapter 3 today. It's a little bit much, so I might actually need 10 or 20 minutes on Wednesday. We'll see how it goes. So let me remind you, I stated this theorem last time. Actually, before I remind you about the statement of this theorem, we did prove last time that geodesics are locally length minimizing. That is, if you stay inside a normal neighborhood, which means the image of so a normal neighborhood means it contains, okay. If you take, if you choose a point P in M, let me draw a picture. If you choose a point P in M, then we know that there's some neighborhood that is mapped onto diffeomorphically a neighborhood of the origin in TPM that is mapped onto diffeomorphically by the exponential map. So because this is an open set in TPM, and I have the norm induced from the inner product GP on TPM, I can take this to be B delta of 0p, an open ball centered at the origin with radius delta, and then this is B delta of P, which by definition is XP of B delta 0. This is called, in fact, what we want is we want the closure to be inside V, where this is a diffeomorphism, sorry, onto XP of V. So we know there's going to be some neighborhood of V where the exponential map is a diffeomorphism onto its image, and then we can choose a ball whose closure is contained in that neighborhood, and then the image of that is called a geodesic ball. Okay, so we proved that as long as you're in a geodesic ball, then we know there is a geodesic joining P to any point in the geodesic ball, and what we proved is that that's minimizing, and that's the unique minimizing curve between those 2 points. Okay, so we proved that in a geodesic ball, so that if Q lies in B delta P, then there exists a unique minimizing curve from P to Q, and it's the geodesic. We know that for any point in here, there is a geodesic because we take the radial curve. Right, if I take a point here, it corresponds to some point in this ball, and we know that the straight line from the center, from the origin to that point, gets mapped to a geodesic from P to Q. And last time we proved that that is a minimizing curve from P to Q among all piecewise smooth curves from P to Q, even if they leave the ball. Okay, so that was a reminder of what we did last time. Now, what we want to show, so we showed that whenever you have a geodesic ball centered at a point, then every other point in P can be in that geodesic ball can be joined to P by a minimizing geodesic. Okay, but we don't know if we have 2 points in this ball whether they can be joined by a minimizing geodesic. We just know that P and any other point, the center and any other point, can be joined by a minimizing geodesic. And this theorem is exactly going to show us that we can make this thing smaller so that any 2 points in there can be joined by a unique minimizing geodesic. And that's what this theorem says. So it says that for any point in the manifold, we can find an open neighborhood, W, and a delta, such that for any point in W, the geodesic ball centered at that point with radius delta contains W. Okay, so any 2 points in W are, what am I saying? Any point in W is contained inside a geodesic ball centered at that point. So W is a normal neighborhood of each of its points. I want to make a remark before we start the proof. We'll see we can take delta as small as we want. It's not going to be relevant. It's not going to be relevant for this proof, right? We just know there exists some delta that this is true. But in the second half of the lecture, I'm going to want to use this theorem with a sufficiently small delta. So in the course of the proof, you'll see that there's some delta, and any smaller delta will also work. Okay, so I'm going to probably erase the picture. Let's start the proof. I did start it quickly at the end of last lecture, but we didn't really get very far. So we'll do it over. So recall, there exists a U containing P open in M and an epsilon positive such that if Q is in U and V is in TQM with norma V less than epsilon, then XQ of V is defined. Right? We can take the geodesic with initial point Q and initial velocity V and follow it for time 1. And this is because the ODE theorem gives you a uniform domain of, so you can find an open set in the set of all initial data where you have uniform time existence. And then by rescaling, you can make that time interval -1 to 1. Okay, and then we had U tilde is the set of all QV in TM such that Q is in U and V is in TQM with norma V less than epsilon. This is open in TM. This is all from 2 lectures ago, I think, when we talked about the exponential map. So let's define a map capital F from this open set U tilde into the product M times M by F of Q and V is exactly Q exp Q of V. So you see, we had to restrict to this open set, so this is defined. This is exactly an open set on which exp Q of V it makes sense. And what is this map? It's a map from a manifold. This is an open subset of the tangent bundle, so it's a manifold, into this manifold. These manifolds have the same dimension. They're both 2n dimensional, and it's smooth because the exponential map is smooth. And what does it do? It doesn't do anything to it takes a point in U tilde, which is a point in U together with a sufficiently small tangent vector at that point. And it maps it to the pair where the first item in the pair is Q itself. And the other one is you take the geodesic with initial point Q and initial velocity V, and you follow it for time 1. Okay, so you see that being in the image of this map F means you can join this point to this point by a geodesic, right? A pair, let's say Q1 and Q2 is in the image of F if and only if Q2 lies in a geodesic ball centered at Q1. Okay, so that's the motivation for this function. And we also note what happens if I take F of P0. So it doesn't do anything to the first point, and then we're going to have XP of 0, which is just P, which is just P. Okay, so this smooth map takes P comma 0 to P comma P. Therefore, the push forward goes from TPM plus TPM to TPM plus TPM linear. And that's because this is up to a canonical identification. This is the tangent space to U tilde at P0, and this is the tangent space at P comma P to M times M. Right? You know from smooth manifold theory that the tangent space of a product is the direct sum, is canonically the direct sum of the tangent spaces. And this is easy to see because this is an open subset of the tangent bundle. So you'll see in the course of the next calculation, it'll be clear why this is true. So we claim that this linear map is invertible. Okay, this is going to be similar in spirit to when we proved that the exponential map, the push forward of the exponential map at the origin was invertible because it turned out to be the identity. This one's not going to turn out to be the identity, but it's going to be still invertible, and then we'll be able to use the inverse function theorem by shrinking u tilde, it'll map diffeomorphically onto some possibly smaller neighborhood of P0 onto its image. And then from there, we'll see why we get the theorem. Okay, so let's compute this push forward explicitly. Every element in here is going to be a tangent, an element in here plus an element in here, right? And this is linear. So if I can see where it sends something like of the form v comma 0 and something of the form 0 comma v, then I know where it sends everything. Okay, so what is the push forward at P0 of 0v? Remember how we compute push forwards in geometry? We have to find a curve. This thing is a curve, alpha of t, in u tilde, such that alpha at time 0, what happens if I put t equals 0 here? I get P0, which is exactly where I want to compute the push forward. And alpha prime at 0 is, this is constant, right? So this is 0v in t P0 of u tilde. Okay, so I find a curve passing through the point where I'm applying the push forward with initial velocity equal to the vector on which I'm applying the push forward. And then I feed that curve into the smooth function f, whose push forward I'm computing, and I take the velocity of this curve. But by the definition of f, this is going to be d by dt at t equal to 0. What happens? How is f defined? I don't do anything to the first point, and then I apply x of the first point to the second vector. So this will be p x p tv, and I take d by dt at t equal to 0 of this, but that's 0v, right? Because that's constant, and this is exactly gamma vt by the rescaling lemma. So I want the velocity at time 0 of this curve, but that's v. Okay, so this map, if I plug in something of the form 0v, I get 0v. So it's almost looking like it's going to be the identity. Let's apply the map to another vector. I'm going to call it alpha prime of 0, 0. So this alpha prime of 0 is in TPM. Okay, well, what do I have to do? I have to find a curve. I have to do d by dt at t equal to 0 of f applied to some curve whose initial point is p comma 0 and whose initial velocity is this. So I claim I can take alpha of t comma 0, because if I call this thing beta of t, this is a curve in u tilde. Where does it go at time 0? I get alpha of 0, 0, which is p, and beta prime at 0 is just alpha prime of 0, 0. Okay, so if I do this, now I use the definition of f again. Definition of f. This becomes the first, nothing happens to the first term. And then I get x. I have to put this thing down here and this thing over here. But if I take the exponential map at a point and apply it to the 0 vector, I just get this. It doesn't move, right? I want the geodesic with initial velocity 0. That's the constant geodesic. So this is d by dt at t equal to 0 of alpha of t, and that's alpha prime of t, alpha prime of t. Oh, sorry, 0, alpha prime of 0. Okay, so we've figured out that this smooth function, when you apply it to 0v, you get 0v, and when you apply it to alpha prime of 0 comma 0, you get alpha prime of 0, alpha prime of 0. We put those two pieces of information together. What have we shown? because it's linear, I can now act on this pair by linearity. I write this guy as this vector plus this vector. And so what I'm going to get is this vector plus that one. So I'm going to get alpha prime of 0 and then alpha prime of 0 plus v. So if we look at this, what does this mean? This is the same as multiplying on the right by this matrix, I, 0. Okay. Because if I do this block multiplication, I get alpha prime of 0, and then I get alpha prime of 0 plus v. Okay. So the 2n by 2n matrix representing this push forward is not the identity, but it's clearly invertible. Okay. This is invertible. I probably shouldn't write this long. I'm going to try not to do it again. So it's invertible. That means I can apply the inverse function theorem. The push forward of capital F at that point is invertible. Let me erase two boards. Okay, so then, by the inverse function theorem, there exists a possibly smaller open neighborhood v tilde inside u tilde of p comma 0 that is mapped diffeomorphically onto its image. Diffeomorphically onto its image, f of v tilde. Okay. But if we go back and look at what u tilde was, this was an open set in the tangent bundle. And you know that the topology on the tangent bundle, if you take a small enough open set in the base and you look at the inverse image, that's going to be a product. The tangent bundle is topologically trivial. So by the definition of the product topology, that means I can further shrink v tilde if I want, by definition of the product topology, to make sure it's a product. So by the definition of the local product topology on TM, by further shrinking v tilde, we can assume that v tilde is of the form q comma v, where q is in v and v is less than delta, for some open neighborhood v of p with v contained in u and some delta positive. Right? But all we're saying is that if you take an open neighborhood in here, this is already a product, right? You can think of if u is small enough so the tangent bundle is trivial over there, this is really just a product of u with the tangent vectors with norm less than epsilon. So I found v tilde as an open subset contained in here. But then that means there's a basis open subset contained in v tilde. And a basis open subset is of this form. It's a product of a neighborhood v of p, which is contained in this neighborhood u, and some small open ball. So delta here is less than epsilon. Okay. And notice, as I said, we can take delta as small as we want. Because if this is true, if f is a diffeomorphism on v tilde, and then if I shrink delta, it'll still be a diffeomorphism on its image. And that's going to be not important in this proof, but it will be important in the second half of today's lecture. Okay, so now I claim we're done. Why are we done? Actually, we have one more step and then we're done. So f maps V tilde diffeomorphically onto its image, let's call it W tilde, which is an open neighborhood of P comma P in M times M, right? That's where F maps P comma 0 to P comma P, and the inverse function theorem tells us it's going to take a sufficiently small neighborhood of P comma 0 in Tm to an open neighborhood of P comma P in M times M. Now again, by definition of the product topology on M times M, there exists an open neighborhood W containing P such that W times W is contained in W tilde. Right? All I'm saying is that W tilde is an open set in M times M containing P comma P. So it contains a basis open set, right? Which is of the form, W1 times W2. And I can take the intersection of W1 and W2, so I can assume that this is a W cross W is in here. Okay, so now I claim that this W and this delta will work. So let's just unpackage what we've done and see why it works. So let's check that this W and delta satisfy the statement of the theorem. So W is certainly an open neighborhood of P, right? Because it is, and delta is a positive number. What we want to show is that W is contained in B delta Q for all Q in W. Okay, that means it's an open neighbor, it's a normal neighborhood of each of its points. That's what the theorem said. Okay, so let's see why this is true. Let Q be in W. So we know that the ball of radius delta centered at the origin in TQM, well, that's a subset of TQM. If I look at Q times W, this is definitely contained in W times W, and this is contained in W tilde, which is F of V tilde. Okay, but F is the diffeomorphism on V tilde, so in particular, it's a bijection. F is a bijection on V tilde, and recall that F of QV is Q x Q of V. It doesn't do anything to the first point, right? So all these points are in here, so they're F of something in V tilde, but the thing that they're F of in V tilde has to have Q as the first argument, because F doesn't do anything to the first argument. So Q times W has to be contained in F of Q times B delta 0. And that, of course, is just Q times X Q of B delta 0, which is B delta Q. Okay, so this says that Q is in B delta, sorry, it says that that W is in B delta Q for all Q in W. Okay, so it's technical, it's a bit annoying, but really what it boils down to is, you write down what you want to do. You want to be able to reach, you want to have a small enough neighborhood of P such that any 2 points in that neighborhood can be reached one to the other by a geodesic. And that's what motivates you to define the map F, because the map F is exactly the map such that the points in the image of F are points that you can reach one to the other by a geodesic. So it looks mysterious. He doesn't Bill Karma doesn't say this is why we define the map F, but if you think about it, it's exactly what you want to do. Right? And then you want to show that the map F is a diffeomorphism. It's not in general, but close enough to p comma 0 it will be by the inverse function theorem. Okay, so let's make a remark.
Question.
About this. Yep. Question. Yep.
I thought W was a neighborhood in the manifold.
It is.
Okay, but the last line you wrote is writing it as a subset of the ball, which is a subset of the tangent space.
No, this ball here, sorry, this ball B delta 0 is in the tangent space. X Q of that is what I write as B delta Q. That's in M. So B delta 0 is in TQM.
Oh, I see. That's a delta. Okay.
And B delta Q is X Q of B delta 0, and that's in M. And this contains 0, and this contains Q. Okay, good. All right, so a remark. It follows from this theorem that given any two Q1 and Q2 inside W, there exists a unique minimizing geodesic of length less than delta joining Q1 to Q2. But let me put it on the other board. But the really annoying thing is that this geodesic does not have to stay in W. But this geodesic need not lie entirely in W. All we know is that it lies in the ball of radius delta starting at Q1, which contains W. Okay. It also lies, because you can go backwards, you can follow the geodesic the other way. It also lies in the ball of radius delta centered at Q2, and that contains W. But this geodesic doesn't have to be completely contained in W. So I'll draw a picture. So there's our manifold M. Here's our point P. What we've shown so far is that we can always find a small enough neighborhood W, open neighborhood of P, such that if you take any 2 points in here, Q1, Q2, there exists a geodesic, a unique minimizing geodesic from one to the other, but it might come out of W. The only thing we know is it lies inside B delta of Q1, which contains W. It also lies inside B delta of Q2, which contains W. But there's no reason for that geodesic to lie completely in W yet. We're gonna have to further refine and make our neighborhoods even smaller so that this is true. Yeah. Well, I'll tell you what. So the question for those of you on the virtual audience is, how annoying is this actually? In practice, this W is going to be good enough for almost all our purposes. But after I prove that we can get what's called geodesically convex neighborhoods, I will tell you that the main application that I know of that is to computing check cohomology. If you know what that is, that every manifold has a good cover where the check cohomology for that cover computes the actual check cohomology without having to take a direct limit. So that is a good application, and I'm sure there are others. But for our course, this is going to be all we're going to need. I'm pretty sure. Yeah. I'd have to think about it. So the question was, can you give an example where this kind of thing happens, right? The reason it's hard to do that is it's very hard to compute exactly what the geodesics are for a given metric, right? The only time we can really do that is if the metric has a lot of symmetry and we know exactly what all the geodesics are. And in those cases, this kind of thing probably doesn't happen. Let's see, does it happen on the sphere? I mean, every example I look at the sphere. Well, yeah, this probably already even happens on the sphere, right? Suppose I take a neighborhood like this. Oh, I want a totally normal neighborhood. This is probably not a totally normal neighborhood. If I go, anyway, if I try to think of it now, I'll get it wrong and we'll run out of time. So let me think about it. But my guess is it's hard to find examples where you can actually see this happening because it's hard to find explicit examples of geodesics. That might work. So yeah, the remark was to just start with a sphere and sort of cut out some small open set. That might work, but I really don't want to get derailed and try to figure that out now because it's probably going to end up in disaster. Okay. So I want to make another remark. The geodesic gamma joining the unique minimizing geodesic joining Q1 to Q2, let me say joining Q1, Q2, 2 points in W, depends smoothly on the 2 points, Q1, Q2, in the following sense. So given Q1, Q2 inside W times W, there exists a unique V in TQ1 of M given by Q1 V is F inverse of Q1, Q2, such that gamma prime of 0 is V. Right? This just follows from the way we prove that you have this geodesic, right? If I take 2 points Q1, Q2 in W, W cross W is in W tilde, which is F of V tilde. So it's F of some unique thing, Q1 times V. And the definition was that if you apply X Q1 to V, you get Q2, right? X Q1 of V is Q2. So this exactly says that if you take the geodesic with initial point Q1 and initial velocity V, then it's going to take you to Q2 in time 1. Okay, so what do you need to know to get, if you want to say, I want I know there's a unique minimizing geodesic from Q1 to Q2, if Q1 and Q2 are in W. In what sense can I say it depends smoothly on these 2 points? Well, what you need to know for the geodesic, you need to know its initial point, and you also need to know its initial velocity. And its initial velocity comes by applying this smooth function to Q1 and Q2, and then taking the projection onto the second component. So V is a smooth function of Q1, Q2 in that sense. Okay, so not only for any 2 points in W do we get a unique minimizing geodesic between them, but in this strict sense, this dependence of the geodesic on those 2 points is smooth. Okay, so as I mentioned, we're going to further refine this to get what's called geodesically convex neighborhoods in a few minutes. But we have another corollary now that comes from this theorem, which is very important. So last lecture, we proved that geodesics are locally length minimizing, right? If you have a geodesic and it lies inside the image of a geodesic ball, then it's minimizing among all curves between those 2 points, even if those curves leave the ball. But what's not necessarily true is that any 2 points have a unique minimizing curve or even a minimizing curve between them. They may not have any minimizing curve between them. And we saw that if you just take Rn and you remove a point, right? If the geodesic from those 2 points was going to pass through the point you removed, now there's no longer a minimizing curve between them. So it's not true that given any 2 points on a Riemannian manifold, there always exists a minimizing curve between them. But let's suppose that there was one. No matter how long it is, we're now going to be able to prove it has to be a geodesic. So let gamma from 0L to M be a piecewise smooth curve parameterized by arc length. Remember, because the notion of the length of a curve has nothing to do with its parametrization. Length is independent of parametrization. So we might as well, if we're going to say something about lengths of curves, we might as well parameterize it by arc length. And suppose gamma is minimizing. This means that the length of gamma, which is L, because it's unit speed, is less than or equal to the length of alpha for any piecewise smooth curve alpha such that it has the same initial and final points. Let me say, let's say alpha from AB to M such that alpha at the initial point is the initial point of gamma, and alpha at the final point is the final point of gamma. Okay, so I haven't finished stating the corollary. But before I finish stating it, let me just say, note, such a gamma need not exist. We are assuming it exists. Okay, so then gamma is a geodesic. In particular, gamma is smooth. It's not just piecewise smooth. It has no jumps in its velocity. Yeah. So there exists curves between any 2 points. Well, if it's connected. If it's not, just take each connected component. But if our so the question is, why did I make this note? So given our manifold, if the 2 points are in the same connected component, there will exist a piecewise smooth curve between them. There may not exist a minimizing curve. There may not exist a curve with smallest length. Because you might always, given any curve, you might be able to find another curve with smaller length. It's exactly what I said. If you take R2 and you take away this point, and you say, is there a smallest curve between these 2 points? I can always make smaller and smaller length curves, but I can never get a smallest one. But the limit's not in there. Right, so this is kind of cheating, right? Because I took a point out. But there are examples where you can't sort of fill it in and make it complete. Yeah. So we'll see that the solution of this, like when can we assume there always exists a minimizing curve between 2 points if the manifold is connected? That's going to be basically completeness, right? That's coming later. Okay, so this is the corollary we want to prove now using our totally normal neighborhood theorem. And you'll see where we use that in the proof. So here's the proof. Let T naught be in 0L. We'll show, okay, and let W be a totally normal neighborhood. That's the W from the previous lemma, previous theorem, totally normal neighborhood of gamma of T naught. Okay, so it's our manifold gamma of L, gamma of 0. T naught is somewhere, it could be one of the endpoints, doesn't matter. Gamma of T naught is somewhere on this curve, and we can find this totally normal neighborhood W. Okay. So there exists a closed interval. Why did I say closed? Well, that's true. There exists a closed interval I contained in 0, L with non-empty interior such that gamma of I is contained in W. So by continuity, gamma is continuous. What do I mean? I can find some closed interval contained in 0L such that everything, all the points inside this orange interval, when you apply gamma to them, they lie in W. And if T naught was at the end, it would be something like this. But it's the same idea. So a non-empty interior, what it just means, it's not a point, right? It's at least it has some positive length. Okay. Now let's look at the restriction gamma restricted to I goes from I and it maps into W. That's how we chose I. And this is a piecewise smooth curve. The restriction of a piecewise smooth curve is piecewise smooth. Piecewise smooth curve joining 2 points in a totally normal neighborhood. Right? Remember, because this W is a totally normal neighborhood of each of its points, this point here, or this point, either one of them, lies inside, they're both in W, and they lie in a geodesic ball center. W is contained in a geodesic ball centered at each of its points. So if this is the point, I don't want to give too many, let's call this thing, do I have any P's here? I don't have any P's. Call this thing P, then B delta P contains W. Okay, so what we know, I'll draw the picture again. W, this is gamma of T naught. This orange thing is gamma of I, and then it continues like this. So by the hypothesis that gamma is minimizing, it follows that gamma restricted to I is minimizing. So why is that? I want to show that if I have any two curves joining these 2 orange points, then the length has to be at least as big as the length of the orange curve. But that's clear because if I take some other curve, it doesn't have to stay in here. If I take some other curve joining these 2 points, then I can follow the pink curve. This is gamma of 0. This is gamma of L. I can follow the pink curve until here, and then this blue curve, and then the pink curve. And by the hypothesis, that length is going to be at least as big as the length of gamma, right? But this part has the same length, and this part has the same length. So if I throw them away, that means this blue curve has length at least equal to the orange curve. So the gamma restricted to I is minimizing, but it lies inside inside W, and we know there exists a unique minimizing curve because these are both inside a normal ball center at any of the points, we know there's a unique minimizing curve joining those 2 points, and it is a geodesic. Yeah. Oh, sorry. Yeah. Sorry. I do want that. Sorry. I want T naught and I. Closed interval I with T naught in the interior of I. Thank you. That was implicit in all the pictures, but I forgot to write it down. Thank you. So hence, by the uniqueness of length minimizing curves, between 2 points in a normal ball, gamma restricted to I is a geodesic. Okay. Oh, sorry, is a reparametrization of a geodesic but gamma has constant speed. So gamma restricted to I is a geodesic. In other words, what am I saying? The uniqueness theorem that we proved last lecture says that if you had any other curve joining these 2 orange points, right, which had length equal to the length of this orange curve, then it has to be a reparametrization of that, right? Sorry, then it has to be a reparametrization of a geodesic, okay? But we're already assuming gamma has unit speed. So if you if it's a reparametrization of a geodesic and it has unit speed, then it's a geodesic. And since T naught was arbitrary, so gamma restricted to I naught to I is a geodesic. T naught is in the interior of I, and T naught here was arbitrary. So gamma is a geodesic. Note what we've proved, right? We proved that any geodesic is length minimizing as long as you take a small enough piece of it, locally length minimizing. And we proved that any minimizing curve, if it exists, must be a geodesic. We haven't proved that a length minimizing curve always exists, because it doesn't always exist. And we also haven't proved that if you have a geodesic, but its length is too big, that it'll be length minimizing. That also is false. We saw that on the sphere, right? If you take a great circle that goes, has length bigger than pi, it's not length minimizing between its 2 endpoints. Okay. Any questions about that? Yeah. Yes. So the question is, what if the curve was just continuous and not piecewise smooth? Bad things must happen, right? We certainly need the velocity to be at least continuous, except for a set of measure 0 to define the length. Okay. So let's only think about piecewise smooth curves. Okay. Good. So the next topic, which is the last topic in chapter 3 of Do Carmo, is the notion of geodesically convex neighborhoods. Geodesically convex neighborhoods, also called strongly convex. I've only seen them called strongly convex in Do Carmo. Probably other texts might say the same thing. I've heard them called geodesically convex. So let's give the definition. So a subset S of our Riemannian manifold is called geodesically convex if and only if, whenever Q1 and Q2 are in the closure of S, then there exists a unique minimizing geodesic gamma joining Q1 to Q2, whose interior is contained in S. I should an open subset, I guess. No, maybe it doesn't matter. Whose interior is contained in S. I guess I want the interior to be contained in interior of S. So all our geodesically convex subsets are going to be open. In fact, they're all going to be, well, they're going to be geodesic balls. So this is going to fix the problem we talked about before, right? So we have S. This is S closure. If I take any two points in the closure, so they don't have to both be on the boundary. One could be inside or both could be inside. There's going to exist a unique minimizing geodesic joining them. And that unique minimizing geodesic, its interior, what does the interior of the geodesic mean? It means the image of all the points except the two endpoints in the interval, right? There's a closed bounded interval, AB, and it means that the image of the open interval AB lies inside the interior of S. So it's always inside S, except possibly at the two endpoints. And it's minimizing, and it's the unique minimizing geodesic between them. This exactly fixes the problem we had before, where we knew in W, for any 2 points in W, there was a minimizing geodesic between them, but it didn't have to stay in W. Okay. So I think we have time to prove that, and then we'll be done with the horrible technical part of the course. Exactly 1/4 of the way through the term. Okay, so we have to prove, so we will prove every point has a geodesically convex neighborhood. Okay, but we need a lemma first. For all P and M, there exists some epsilon positive such that any geodesic in M that is tangent at Q to the geodesic sphere X P BR0 for of radius R less than epsilon stays outside of XP BR0 for some neighborhood of Q. So what does this say? It's a very strange looking statement. I'll draw a picture. Okay. So this is the point P. I'll draw the picture, you know, in TPM, really. Well, it doesn't matter. This is B epsilon of P. This is B R of P, where R is strictly less than epsilon. So I'm saying that if you take, so there exists some epsilon. For every P, there exists an epsilon. That'll depend on P, such that if I take a geodesic that's tangent at a point Q to to this geodesic sphere, then near this point of tangency, it has to be outside of the pink geodesic sphere. So it can't, and you know, you can see from the picture, of course, this has to be true from the way I drew the picture, right? If you're thinking in terms of Euclidean geometry, if you think of these, just think in R2 and think of these geodesic spheres as being circles of, you know, constant radius. If we were in the Euclidean space R2 with the Euclidean metric, then the geodesic balls are just circles, are just ordinary balls, and the geodesic spheres are just circles, and the geodesics are straight lines, right? So we know that if you have a straight line tangent to a circle in R2, it stays outside of that circle. It's just tangent at that point. It can't go inside. And similarly, if you have a sphere in Rn and you have a straight line that's just tangent to that sphere, it's going to stay outside everywhere. What we're saying is that, you know, this is a hint of what's going to come in a week or so that says that in a Riemannian manifold, as long as you're close enough to that point, the metric is close to the Euclidean metric, right? You need to really go further to see differences in the geometry. You can't see them up close. And because this is obviously true in Euclidean space, then at least if we make epsilon small enough, there has to be an epsilon small enough such that if you're, you know, if you're in a geodesic ball whose radius is less than epsilon, if you have a geodesic tangent to the sphere, then it stays outside. It could come back in later, right? It might do this, because we don't know what happens to the manifold geometry far away, right? But at least close to Q, this geodesic stays outside of this geodesic sphere. That's the statement of the lemma. And again, Del Carmo doesn't really motivate, like, why would this lemma be true until you think, well, it's obvious in Euclidean space. And so if we want to think that Riemannian manifolds in a small enough neighborhood should in some sense be basically the same or close to Euclidean space, this should also be true. Okay, that's the intuition. All right, let's prove this, and then we can, as a corollary to this, we'll have our geodesically convex neighborhoods. So let's let W be a totally normal neighborhood of P. So we know that W is contained in B, BQ delta for all Q and W. And there exists a delta such that every point in W lies in the geodesic ball centered at that point of radius delta. So hence, if gamma V is a geodesic with initial point Q, and initial velocity V with V less than or equal to delta, then gamma V is defined on an open interval containing -1,1. Right? We're just saying that every point this, you know, what does it mean to have a geodesic ball? We only consider geodesic balls as the image under the exponential map of an open ball whose closure is still contained in the domain where the exponential map is a diffeomorphism. So the closure of this is still in the image of the exponential map. And that means if I have any V with length less than or equal to delta, then I can apply the exponential map for time 1. Okay, so that means that this geodesic is defined at least on -1,1. So by rescaling, by the rescaling lemma, there exists some zeta positive such that gamma V is defined on -zeta zeta for all Q in W, V in TQM, such that the length of V is 1. Okay, so what am I saying? If the length is sufficiently small, we can define it for this big time. Okay, I want the length to be 1. So we know that if we want the vector to be longer, the interval is defined for less time. But because I can get this uniform length bound in W because of the totally normal neighborhood, that means I can find this uniform interval of existence for all unit speed geodesics with initial point in W. It's worth saying that again. So what this means is, i.e., because W is a totally normal neighborhood, there exists a uniform minimal interval of existence minus zeta zeta for all unit speed geodesics with initial point in W. Okay, so I don't have to worry that maybe as I'm moving, towards the edge of W, the time interval for which my unit speed geodesic can exist might shrink down to 0. Right? I can get this zeta, which works for every unit speed geodesic starting at a point in W. That's where I'm using the totally normal neighborhood. Now, let's let T1W be all of those pairs QV, where Q is in W, V is in TQM, and V has length 1. Right? It's the unit sphere. You take the unit sphere inside TQM for all the Q's in W. And let's let gamma be defined on minus zeta zeta times T1W to M be, so I need a time, a point, and a velocity, an initial point in W, and an initial velocity which has length 1. And I send that to gamma VT. This is the geodesic with initial data Q and V. Okay, and I exactly had to use this normal neighborhood to make sure that I can take this same minus zeta zeta for every point in here. So this is a smooth map. Gamma is smooth on minus zeta zeta times T1W, because remember, the dependence, this is basically it's coming from the fact that the exponential map is smooth. Okay, so we're almost where we want to be. Let's let gamma hat from minus zeta zeta cross T1W to TPM be gamma hat of TQV is equal to X P inverse of gamma of TQV. This is also smooth. Remember, everything here is happening in a normal neighborhood, so I can, the exponential map is a diffeomorphism, and so the inverse is smooth. So I'm taking the smooth composition of two smooth functions, so this is smooth. So let me just say, so notice, since Q is in W, there exists a radial geodesic from P to Q. So that means Q equals XP let me not say this. It's going to be too confusing, actually. Right. What I wanted to explain is why we know that this point is in the image of XP. So you can check for T sufficiently small, gamma TQV is in the domain of XP inverse. So this is okay. Because I'm actually going to fix Q and V, and I'm only going to care about the derivatives of gamma hat at t equals 0. So it's definitely fine for small enough t. This gamma is defined for all t in the minus zeta zeta. So De Carmo here is a bit sloppy. He doesn't really explain why gamma hat. I don't think for any Q and V, I'm not sure if gamma hat is defined. Okay, so let me say remark. It's not clear if for a given Q and V inside T1W, that gamma hat is defined, let's say gamma hat of dot QV is defined for all T in minus zeta zeta, but it's easy to check that it's defined for all T sufficiently small. And that's all we're going to need. It's possible, I couldn't figure it out. It's possible that this works for all minus zeta zeta, but it's not important. Okay, so now we're almost done. Define a map capital F. Again, so I'm being a little sloppy here because this might have to be smaller. Q and well, let's do it this way. Okay, so some minus, what's your, let's say eta FQV. I'm going to call it F. So fix Q and V inside T1W. Okay, define F by F of T is gamma hat of T Q V squared. This is the norm squared in TPM because gamma hat maps into TPM. Okay, so why do I care about this? Because remember I had this picture. Let's draw the picture now in TPM. So this is the ball of radius epsilon centered at 0. We haven't picked epsilon yet. We're gonna pick it. This is what we want to prove, right? And this is BR0. And we want to say that if we have a geodesic, which is just tangent to the sphere, that it's going to stay out of the sphere for a small enough time. And what is this? So this thing here will be gamma hat of TQV. This is the image of Q. Q is X P of V, because V is length 1. This is V, and this is the 0 vector inside TPM. This corresponds under the exponential map to having P here, and then B R of P, and then B epsilon of P, and gamma coming in at Q tangent, where Q is X P of V. Okay, so what is this function F telling us? It's taking the gamma hat of TQ, it's taking the distance from the origin to this pink curve. So F of T is the distance squared in TPM with the norm GP from 0P to gamma hat of TQV. Okay, and what we want to say is that for small enough t, because at t equals 0, it passes through here. For small enough t, the distance is no less than it is here. That'll tell us that the red curve lies outside the blue, and that means the image here this red curve will lie outside of this geodesic ball. Okay. So,
Small point.
question? Yeah.
It looks like you're drawing the arrow on the x function going from the manifold to the tangent space.
Oh,
Is
yeah,
that the
yeah.
other way?
Thank you. Yeah. Thank you. Yeah. Okay, so this f is smooth as well, right? Because gamma tilde is smooth, the norm function is smooth, norm squared is smooth. That's why I have to take the square, because otherwise I'd have to worry about the square root. So let's compute what's df dt. This is the inner product of gamma hat with gamma hat. Remember, I'm fixing q and v. I'm just thinking this as a function of t. Df dt is going to be 2 d gamma hat dt gamma hat, right? Everything is happening in this. This is a function into a fixed vector space with a fixed inner product. And d squared f dt squared, I just have to differentiate this with respect to t. So I'm going to get 2 d squared gamma hat dt squared gamma hat plus 2 d gamma hat dt norm squared. Just differentiate that. Okay, now since gamma, oh no, so everything I've done here was for any geodesic, right? Now suppose gamma is tangent, sorry, before I do that, let R be positive such that the geodesic sphere BR of P is contained inside W. We can certainly do that by continuity, okay? Because W is open and X is continuous. So suppose gamma is tangent to the sphere XP of the boundary D of the ball of radius 0 at Q, which is gamma of 0 QV. Okay, so by the Gauss lemma, d gamma hat dt at 0 QV, inner product gamma 0 Q gamma hat 0 QV is 0. The Gauss lemma is exactly telling us this, right? It said that we used it the other way when we proved it. We said if you had a picture in TPM where you had a curve which was tangent to the sphere, a vector which was tangent to the sphere, right? Then it was orthogonal to the radial geodesic going out, right? Sorry, the assumption was if you had a vector tangent to the sphere in TPM, so therefore by the definition of what the sphere is in TPM, that means it's orthogonal to the radial vector, then the image under the exponential map had the same orthogonality, right? This line gets mapped to a geodesic, and there's a right angle here. So now that says that there's, in some sense, it's almost an isometry, right? It preserves the angle. It preserves these angles, right? The angle between radial geodesics emanating from P and vectors which are tangent to the geodesic sphere. But we're using the Gauss lemma in the other way now. We're assuming that we have this geodesic gamma, which is tangent to the geodesic sphere, so that its image under the inverse of the exponential map, the push forward of the inverse, or the inverse of the push forward, it's the same thing, we're gonna have a right angle here, right? So this is just saying that the velocity of this pink curve is orthogonal to there, right? If gamma is tangent to this geodesic sphere, that means its image under the exponential inverse of the exponential map, gamma hat, is tangent to this geodesic sphere. Okay, so we're almost done. So hence, df dt at 0 QV is 0. Right? This is exactly, if I plug in t equals 0 here and q and v are fixed, this inner product being 0 tells me that f vanishes at t equals 0. The first derivative of f vanishes at t equals 0. So t equals 0 is a critical point of the map t goes to f of t qv. So if we can show that the second derivative at 0 qv is positive, then f has a strict local minimum. At t equals 0. So f of dot qv. Okay, and that's exactly what we want, right? Because it says that for t sufficiently close to the origin, f, the values of f will be bigger than they are at t equals 0. And therefore, the gamma hat will be outside of this blue ball, close enough to here, and therefore its image will be outside. So this would complete the proof. So why is that true? Okay, so why is that true? This will be true for r sufficiently small. To see this, suppose we take q equals p. Okay, then what is gamma hat of t pv? I have to see, where's the definition of gamma hat? It's gone, right? I take gamma of tqv do you take the geodesic with initial point q and initial velocity v, and you follow it for time t, right? But if I take initial point p, then I know that under the exponential map, the geodesics with initial point p become exactly those radial geodesics emanating from the origin. So this is exactly tv, because it's exp p inverse of gamma vt, okay, where v is in tpm. So for when q is equal to p, this function is really simple. So f of t pv is just the norm of tv squared, which is t squared, norm of v squared, which is t squared, because the norm of v is 1. So hence, d squared f dt squared at 0 pv is 2, right, which is positive. So by continuity, as long as I'm close enough to p, right, everything is smooth. So d squared f dt squared is smooth, therefore continuous. By continuity, there exists a neighborhood v containing p with v in w such that d squared f dt squared at 0 qv is positive for all q in v, v in tqm with v length 1, right? I'm saying we know it's positive here, so as long as we're close enough to this point, it's still going to be positive. So now let epsilon be positive such that this ball is contained in V. Hence, if gamma is a geodesic in B epsilon of P, that is tangent to the geodesic sphere exp p d b r 0 of radius r less than epsilon at gamma of 0 q v, then we have a strict local min of f at 0 QV, because we've made this epsilon small enough so that everything that's happening in here is going to have this property that the second derivative will be positive. The first derivative will always be 0, the second derivative will be positive, so it'll be a strict local minimum. Hence, by the definition of f, the points of gamma stay outside xp of br of 0 near q. Okay, so there was one more thing I wanted to do, which will take 5 minutes, but we'll leave it for Friday. So remember, what we want to prove is that we want to prove that every point has a geodesically convex neighborhood, and then I'll make a comment answering the question about what are geodesically convex neighborhoods good for. Okay, so next time we're going to start with the proof that every point has a neighborhood which is geodesically convex. I'll remind you of the definition of geodesically convex. I'll remind you the statement of this lemma, and we're going to use this lemma to give a 5-minute proof of the existence, right? And I'll make a remark that it's related to check homology. So that's going to take really 5 to 7 minutes. And then we're going to start chapter 4, which again, I'm going to assume is a review for most people, even though it might not be. So I'm going to talk about what is curvature, Riemann curvature, Ricci curvature, scalar curvature. And then we're going to move on and spend the rest of the term seeing how curvature and geodesics are related, right? Knowing something about curvature tells you something about geodesics and vice versa. That's the point of the course. Okay, any questions before we stop?